Everyone. Today we're going to be starting chapter 7, which is our t-test. But before we talk about chapter 7, I just want to take a step back and talk about the power curves that we were talking about before in the last class. When we derived all of those examples with our power curve, and we came up with this as a power curve here, this is like a sample power curve for when I have my hypothesis, okay, and I have my true mean that's going to be greater than my hypothesis. So this would be like our right-tailed test, or like we've got our hypothesis and the true mean is on the right-hand side. So our power curve is going to look like this. Now, for example, if we have a case where, say, our hypothesis, our mean here, this is our hypothesis, this is our null hypothesis, right? And then say our true mean is here, right? This is mu, our true mean. Okay, so we would do all of the calculations that we would get, right? Our mean hypothesis, our z values would be negative, but then our true mean z values would be positive because it would be on the right-hand side, whereas on our hypothesis would be on the left-hand side. Our power curve is going to look like this. It's going to go down, so it's going to look like that. Okay, so when we had a right-tailed test, our power curve looked like this. Okay, when we have a left, and when I say left-tailed, I mean this is our hypothesis, and then our true mean is to the left of it. So the power, right, increases as our true mean gets less, farther less than our hypothesized mean. Now imagine, you think you have a homework problem that's like this. Now imagine if we have a two-tailed test, where let's say my hypothesis, I'll put my mu, I'll put h naught, my mu there. Let's say I've got a true mean that could be here, or a true mean that could be here. This is our two-tailed test, right? So this is going to be our left-tailed test. The other one was our right-tailed test. This is our two-tailed test here. Okay, so this is our mean, our true mean. We don't really know where the true mean is, right? So we're going to try out different values of where our true mean could be. If it's a two-tailed test, we're going to try out values that are greater than, we're going to try out values that are less than, okay? So now, my power curve, you're going to have a homework problem like this. My power curve, right, as I'm farther away, I'm high up. As I get closer to my hypothesized mean, the power goes down because the hypothesis and what I think is my true mean, they sit really close to each other, almost right on top of each other. Okay, which means I can't tell the difference, significantly speaking, right, between these two values. Okay, and then as I get farther away on the other side, my power is going to go up again. Okay, so this is our power curve here. Power curve. Okay, so keep that in mind. There's no one true power curve. It's basically going to be based on what type of test you're doing, two-tailed, okay, left-tailed, or right-tailed, okay? And so now, you know, you want to be taking a look at, like, I'm going to be pulling apart my true, what I think is maybe my true mean, right, from where my hypothesis is. My power is going to go up as those things get farther apart because the significant difference between them gets bigger. Anyway, so keep that in mind, right? Because I think this is like a homework problem. You're going to see a power curve like this. You're going to need to try true mean values on either side of your hypothesis mean. Okay, so I just want to call your attention to that. That was from stuff from the previous chapter section about power. Okay, all right. So let's talk. This is chapter 7. And before we get started on that, let me write it down so we can keep track. And so this, I'm covering chapter 7.2, 7.3, and 7.4. They're all about the t-test. You'll notice if you take a look in your book, 7.2 just kind of talks about it in theory. 7.3 kind of dances around stuff. 7.4 kind of gets into the nitty-gritty. 7.4 is where you actually have homework problems that you need to work through. But in my lectures here, I've kind of lumped them all three together. I'm not going to, you know, be separate. Now we're in chapter 7.2. Now we're in chapter 7.3 because they all kind of blend together. So today I'm going to start introducing. We're going to talk about what is the t-test, how we can actually run statistics on it, and then how we can talk about the confidence intervals on it too. Okay, so a couple of the things I want to make note of, so you guys can take a look on our Blackboard page. I put up there a formula sheet. Okay, it looks like this on the front page. There's a lot of stuff down at the bottom. This is probably more than you need to know. And then here's some things on the back. Okay, these are things that when we took the class in person, I would pass out. Students would get this plus a page of their own to take to exams. And you'll notice that there's a lot of other stuff in here that maybe, you know, you've been using so far already. And then there are things for confidence intervals, proportions, for means, things like that. Okay, so this is for you. That's up on our Blackboard page. You're welcome to print it out just to kind of make sure that you're thinking about the formulas correctly. Okay, that the things that you have written down in your notes are, you know, correctly written. Also, because we're talking in chapter 7 about the t-test, which is actually, when you do experiments, you're going to be probably most likely be using the t-test, because the t-test, as we're going to find out, works with the sample. So we think our population has a value of a mean and a standard deviation, but all I really know for sure is the sample that I've gathered, right? And the sample that I've gathered has a mean and a standard deviation because I can calculate those. So we would be doing t-tests, okay, which are an awful lot like z-tests, only they deal with samples. Well, we're going to go into the details. On your Blackboard page, there are 2 different t-tables from different books. This is from a book that I like. It's kind of nicely written. It has our degrees of freedom, but the degrees of freedom, basically once I get above 30, right, then it jumps by tens, and then after about 1,000, once we get up to, oops, sorry, you can see that, after about 1,000, we're getting up, we're going to learn about degrees of freedom in a minute, but then that's basically your z value. And it talks about confidence levels. You're welcome to use this one too. This one here I also scanned, and this comes from the back of our book. Okay, this is the, it's called T-Table Larson book. That's the name of the textbook for this class here. And you can see it's, they kind of don't have as many probabilities. Like we have a lot of probability values here. This is our alpha values. So the probability values go down in a pretty fine grained. Here we don't have as many, okay? But we've got a lot of degrees of freedom. So basically we're enumerating all the degrees of freedom up to 100, and then it jumps to infinity, okay? So I'll probably end up using the one at the back of the Larson book, but I thought I would give you both just to be able to see it. I'm also we're gonna talk about, I've got my Z table here. I want to be able to call your attention to the differences between our Z and our T table, and then how we need to think about this stuff as we're working through these problems. Okay, so these are the things that you'll want to have printed out, in addition to your lecture examples for chapter 7, okay, because we're going to be working through those today as well. Okay, so have these out so that you can read them as we're working through the examples, okay? All right, so with that said, let's go ahead and get started on chapter 7. So basically, we're going to be talking about, this is called the t-test. So this is an awful lot like our z-test, okay, in which we're comparing some kind of a population mean to a sample mean, okay? And then we've got like sample means, sample standard deviations, and numbers in our sample size, and we have what we call degree of freedom. All these things are going to be clear in just a minute. So we want to talk about when we need to use this. Want to use our t-test, sorry. So when are we going to use our t-test? Okay, that's a big question, right? So when we use our t-test is this. I'm going to use it when our distribution of our random variables is approximately normal, right? Remember, our normal is our bell-shaped curve, okay? So let's write that down. This is a bell-shaped curve, and it's symmetric. Symmetric about our mean, okay? Symmetric curve, symmetric about the mean, okay? That's on the graph. We always see that, like our bell-shaped curve, right? Right, and our mean here is right at the center, and this is a symmetric graph, just like our z table, z curve was too. What we notice about the our normal distribution is that the important thing is that our mean, our mu, our median, and our mode are all equal to each other, and they're all equal to 0. We say it's equal to 0, and why is that? Because remember, our normal distribution, right? Right, our standard normal distribution has a mean of 0 and a standard deviation of, a variance equal to 1. That's our standard normal table. Okay, so they're all equal to 0, and they're all at the center of our curve. So this is right here. So this is our mean, our median, and our mode are all here. Remember before when we were talking about basically, you know, different probability density functions, should we use the mean or the median? If there was a big asymmetry in our probability density function, the median was going to be a better bet. Well, here in our normal curve, one of the reasons we like the normal curve is it's so symmetric that our mean and our median sit right on top of each other. They're equal to each other. Okay. Center of our distribution. Okay, remember these graphs here represent our probabilities, right? The area under our curve is our probability. And also, like we did with our z table too, our curve is asymptotic to the x-axis, right? It's going to go on forever, right? But it's never going to hit the x-axis, right? It never actually crosses the x-axis, never actually equals the x-axis, but it basically asymptotes out at the x-axis. All right, so let's talk about how these things are different. How is this different from our z distribution, our z table? Okay, so the thing that makes our t different from our z is that the variance is greater than 1. Okay, that's important because on our standard normal table with our z test that we're doing, the mean was at 0 and our variance was equal to 1. That was the normal n, parentheses 0, 1. Okay, that's our z. Here with our t-test, right, the variance is greater than 1. This is based on what we call degrees of freedom. We're going to talk about what that means later. Okay, the degrees of freedom is actually related to our sample size. We're going to define that out in just a minute. Okay, so one of the things that also happens with our t distribution is as our sample size gets bigger, okay, as our sample size gets bigger, our t distribution approaches basically becomes equal to our z distribution. Okay, so the rule of thumb essentially for using our z versus our t is that we're going to use our t table for n less than or equal to 30. That's always a good bet. It's also true, we're going to actually write this down specifically too, that we're going to use this when the variance is unknown. Okay, these two are really important, right? So if our n is small, say for example, or our variance is unknown. Okay, so let's just actually codify that last part. So sigma squared, our variance is unknown. This is going to be our population variance, right? Remember how we were doing these examples before, and essentially we had a case where like we knew what the mean was, the population mean, but we didn't know what the population mean was, but we knew the population variance. So that's really unusual. We were doing that as an example, okay? But now in reality, we don't know what the population mean is. We don't know what the population variance is. So we need to use the t-table, t-test. Okay, so all that we know is our sample variance, which is more like reality, right? So we have a sample, we gather a whole sample of data. We can gather the mean on the sample, and we can gather the variance on the sample. And we're going to use those to compare things against what we think our hypothesis is for our population mean, okay? So in terms of what this thing looks like, let's draw a picture, our background data, and then how the z and the t sit on top of it. So we're going out, we're gathering a lot of data. Usually this is, remember, binomial in the background, right? We have Bernoulli trials. So I've got all of my data, yes, no data, kind of piles on top. Our law of large numbers says things center around the mean. So let's draw this out right here. Let me make this centered. So this is, we've gathered a lot of data. Completely symmetric, and I'm not the best artist, so bear with me here. Okay, so now what happens is this. I'll draw this out in red and in I'll draw it out in red and black. So my black is going to be my z. Okay, so this is my z distribution. Okay, this is still a normal, right? This is our normal with mean 0 and variance equal to 1. And now our t table, our t distribution kind of looks like this. It's really, really close to our z, but what happens is our tails, the tails are thicker. So this is our t distribution. Right, and I'll write it over here. And here our tails are thicker, they're a little bit wider, thicker than the Z distribution. Why? Because we only have sample information and the sample sizes tend to be small, right? They're smaller than our general population. Okay, so then the variance is not going to be equal to 1. So, right, so our tails are going to be thicker than that. Okay, but this is still essentially a normal distribution, but our variance isn't equal to 1. So let's write down what this our formula is for it. It's going to be really similar. You'll recognize lots of it, like this general shape of it. Okay, so in terms of our t-test, our formula looks like this. E is equal to x bar minus mu over s over radical n. So everything is the same. This is our sample. This is our maybe our hypothesized mean. Okay. This s here represents our sample standard deviation. So that's a change from what we had before. Before we had our population standard deviation. Now we just have our sample standard deviation. So in order to look up things on my t-table, right, I need to do it by degrees of freedom. So let's write down what our degrees of freedom are going to be. So our degrees of freedom are equal to n, our sample size, minus 1. Right, so if I go out and I gather a bunch of data, I gather like 10 samples of data. My degrees of freedom are 10 minus 1, it's equal to 9. I'm going to use that on my graph. See this df, that's my degrees of freedom. I go down here to 9, and then I look over accordingly. And we're going to talk about how we're going to read this in just a second. Okay. So our degrees of freedom is our sample size minus 1. Okay. And we use this when our variance, our population standard deviation, or population variance is unknown. Okay. And then if our sample size is greater than or equal to 30, okay, and the population is normally distributed, okay, oh, n is greater than or equal to 30, well, maybe I can use the z-table. Well, but the z-tables for when I know what the population variance is, but sigma is unknown. This is the most likely case, right? We don't know what the population standard deviation is, so I have to use my t-table. Okay, so let's talk about how we're actually going to read our t-tables, because it's different than our z-table. Okay, remember on our z-table, right? Let's talk about first our z-table so you can remember. The z-table was the area underneath our curve from z, right? This is the z value that we calculated, the z value we get from our alpha, say for example, and it was the area to the left of our curve, okay, always. And it's still always the area under it is equal to 1, right? How we read this was, this is our z value, right? This is 2.61, say for example. This here gave me my probability, which gave me the area to the left of my z value of minus 2.61. Minus 2.61 was 0.0045. That was the area to the left of that z bar. Okay, so this whole table here is a table of probabilities. Okay, now what happens is my t-table, this is listed on degrees of freedom, which we calculate from our n. This across the top here is our alpha value. Okay, and this is a table of t values. Okay. Also look here on our graph, okay, it's still a symmetric bell-shaped curve, okay. Our t value, okay, denotes this point on the graph, right, that corresponds to our alpha and our degrees of freedom, so it's t alpha comma degrees of freedom, and it's the area to the right of that t value, okay. So that would be our alpha value, that's this value here up at the top, and these are the t values that correspond to that particular alpha. So no longer am I looking at the table, getting out the exact area under the curve, the probabilities. This is the area under the curve, and these are the t values associated with that, okay, and the degree of freedom. So I'm going to write it down. I'll draw it down here just so that you can think about it. So we've got degree of freedom. We've got our alpha. So this is 0.2, 0.15, 0.10. 0.05 and so on and so forth. It goes down. So this is 1, 2, 3, and then it goes so and so forth down. Okay, so now let's draw this out. Right, so here's our 0 in the middle here, and this is our, we call T alpha, degrees of freedom, okay? And that's the area to the right of that. This area here is equal to alpha. That's this alpha here up at the top. Okay, so this is what our table looks like. So now when I look at this, right, if I have a degree of freedom equal to 3, and I have an alpha equal to 0.05, I'm going to read it over here, and I'm going to take this t value here. So if I go, let's go up to my degree of freedom equal to 3, I have an alpha 0.05. My t value corresponding to that is 2.3534. That's my t value. 0.3534. Okay, that's how I'm reading this graph. So let's talk about right hand, left hand, you know, right-tailed, left-tailed, and two-tailed, how that's going to work. So, so for example, on a right-tailed test, right? This is a right-tailed test where I've got my hypothesis, my alternative hypothesis, something's greater than. Okay, so my right-tailed test says I need to find a critical value for t, right? That's my goal here, right? And we're going to say our degree of freedom is equal to 16. So that means our sample size is 17. Our degree of freedom equals 16. Our alpha equals 0.05. Okay. So the t value that I'm going to use right here is, I'm going to look this up. Degree of freedom equals 16. Okay. My alpha equals 0.05 right here, right? It's this 1.7459. And because it's right-tailed, it's positive 1.7459. So this is, right, this is my t equals positive 1.7459. I'm really belaboring this point because it's going to be important how we read this table correctly. This alpha here, area under the curve, is 0.05. That's the area, okay? Here, if we do a left-tailed test, we're looking for our critical value for t, okay? And here we have a degree of freedom equal to 24. Let's give ourselves some room. Equal to 24, okay? And it's a left-tailed test. This is alpha equals 0.01. Okay, so how am I going to read this? So I'm going to go to my table. Degree of freedom equals 24. That means that my n, my sample size, is 25. So my degree of freedom equals 24. These both in here. So degree of freedom equals 24. And my alpha equals 0.01. Watch out, this is 0.1, this is 0.01. So I'm going to read this whole column down, right down here to 2.492. T equals 2.492. Now watch out, before you commit to that, let's take a look. This is a left-tailed test. This is 0. This is alpha equals 0.01. Right here, that's our area. This t is our alpha and our degree of freedom. Now, it's a left-tailed test, which means because of symmetry, I have to make that a negative 2.492, okay, because this is positive, t-values, these are negative t-values, because this is our 0, okay. For left-tailed test, t is equal to negative, right-tailed test, t is positive. So let's do a two-tailed test, okay. So now on a two-tailed test, how we do this is, if I've got, we're looking for a critical value for t. What's that going to be equal to? That's what I'm looking at in my graph. So in this case, my degree of freedom is 18. These are just examples. My alpha equals 0.1. Okay. So a two-tailed test, remember, goes like this. This is 0. I'm looking for a t value here, and I'm looking for a t value here. Okay, so I'm going to get a negative and a positive t value. Okay, so our table doesn't specify for two-tailed, so we have to do some calculations on it. So I'm going to take my alpha divided by 2, right, because the alpha is spread across these two regions here. So my alpha divided by 2 is going to be 0.1 divided by 2, which is 0.05. That's what I'm going to use to look up on the table. Okay, look up 0.05. Okay, and my degree of freedom is still 18. So I'm going to look up 0.05, and my degree of freedom is 18. I get a t value that says 1.734. Okay, but it's two-tailed, so I have a positive t and a negative t. right, in order to compensate for both. Have a positive and negative. So keep that in mind. Right-tailed, left-tailed, two-tailed. You have to kind of think about, right? Our whole graph just shows right-tailed. So I have to be able to do some calculations when I'm doing left-tailed and two-tailed, okay? So keep that in mind. All right, with that said, let's look at our lecture example notes, okay? So example 1, we have a medical investigation claims that the average number of infections per week at some local hospital near them is 16.3. A random sample of 10 weeks, so this is our n equals 10. I'm going to start making notes. Had a mean number. This is our sample mean. Sample mean equals 17.7. So sorry, x bar. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at alpha equals 0.05? And we're going to assume that the data is normally distributed. Okay, so let's do like we always did. I'm going to write down our hypothesis. Okay, we're getting this from the way things are written in the question that's being asked. So the hypothesis, our null hypothesis, states that the mean is equal to 16.3, right? So this is our claim. So they claim that the average number of infections at them is 16.3. I'll just write down this right here. So this is versus our alternative hypothesis. Now they don't say, is it greater than, is it less than? They're just saying, are they different? So that means it's going to be two-tailed. Are they different? Okay, it means it's a two-tailed test. Okay, so keep that in mind when we go to work on our critical values. Okay, so the next part is we have to figure out what our critical values are. And I'll say critical values because it's a two-tailed test. I'm going to need positive and negative. Okay, so this is our two-tailed. Okay, and our degree of freedom is n minus 1, so that's 10 minus 1, which is equal to 9. So keep that in mind. We're going to use 9 on our table to look it up. Okay, so now I have to take my alpha and divide it by 2. So my alpha was 0.05. I'm going to divide that by 2. I'm going to get 0.025 with the degree of freedom equals to 9. So I'm going to look that up on my table. So I say degree of freedom 9 and alpha 0.025 is right here, 2.2622. And that's how I'm reading my table. So my t value, my critical values are positive and negative 2.262. Okay. That comes from my alpha and my degree of freedom. That's our table. Now we have to calculate our test statistic. This comes from that formula that we came up with for t. So t is our sample mean minus our population mean. This is our hypothesis. Okay, all over the sample standard deviation divided by the square root of the number of samples that we have. So let's plug in. So our sample mean is 17.7. Our hypothesis mean, our population is 16.3. All over our sample, 10, oh, sorry. Our sample, this is 1.8 divided by radical 10. Sorry about that. Ignore those parts. Okay, so let's calculate it. So our test statistic is 2.460 on the positive end. All right, so what does that mean? Our critical values and our test statistic. So I need to use that to make a decision. I'm just going to draw a quick graph here, right? So I've got my t value. My t is 2.262, and then I've got minus 2.262. These define our critical regions. This area is 0.025. This area is 0.025. Okay, we're not doing p-value method. We're doing our critical value method. So now I got 2.4. So 2.4, or our t equals 2.460. Right here, if you can see how it falls within our critical region. Okay, so now I'll write it out. So let's say our test statistic, which is 2.460, is greater than our positive critical value, which was 2.262. Therefore, what I can do is I can reject the null hypothesis. Okay, which means I'll write it in words. I can, oops. There is enough evidence to reject the claim that the average number of infections per week is 16.3. That's what we're rejecting. Okay, but we need to specify it. What's our hypothesis? What's our critical value or p-value if we're going to do that? Our test statistic and our decision. You have to state those different things in order to get full credit for stuff. All right. So example 2, I'm looking at. So example 2 says, medical researchers found that people who take aspirin take on average 8.6 tablets per week. Some medical doctor wanted to find out if yoga would be able to reduce people's aspirin intake per week. A random sample of 12 people, so this is our N equals 12, who take aspirin were taught yoga. And then after a 12-week period, they had to train them with yoga and do the stuff. Here's their aspirin intake for one week. So we will need to calculate our sample mean and our sample standard deviation. I'm just going to give it to you, but we will need our sample mean and our sample standard deviation from our data. Okay, we're going to test this claim at the alpha 0.1 level, and we're going to assume that the data is normally distributed. Okay, now our hypothesis is this. We're going to say our null hypothesis is that the mean is 8.6 tablets per week versus our alternative hypothesis. Remember, the person said they wanted to see if yoga would help them reduce, right? So reduce tells us it's going to be a left-tailed test, and our mean is less than 8.6. Okay, so this is going to be a left-tailed test. So now we have to calculate out our critical value. And I'll write down this is a left-tailed right from here. So it's going to help us figure out, I need to use a negative t-value, okay, because it's left-tailed. So my degree of freedom is my n minus 1, 12 minus 1, which is equal to 11. I'm going to use that 11 to calculate things on my table. Okay, my alpha equals 0.1. I don't have to divide the alpha by 2 because it's simply just a left-tailed test. Okay, so I'm looking this up on my table. Right, so degree of freedom equals 11. My alpha equals 0.1. I'm looking right here. Okay, so I get my critical value, my test statistic, but it's going to be negative because it's on the left-hand side, minus 1.363. My table only gives it to me as positive, so you need to be able to think, oh, it's a left-tailed test, I have to make it negative. Okay, so be careful about that. Now we get to calculate out our test statistic, which comes from our sample data. Comparison of the sample data to our hypothesis. So our sample mean, right? So taking the sample mean here, so add up all those values, divide them, take our sample mean, 6.8. Okay, our sample standard deviation, S, is equal to 2.37. You guys can go calculate that if you want. I did that for you ahead of time, so we don't have to worry about calculating those things. This is kind of like when you were gathering data, you'll need to count up how many pieces of data, N, your sample size. From that data, take the mean, or sample mean, and from that data, take the standard deviation. That's going to be your sample standard deviation. Now we're going to plug that into our T, bar minus mu, all over S, over radical N. Okay, so let's plug these things in. So 6.8 minus our hypothesis, 8.6, all over our sample standard deviation divided by radical 12, right, our N. So these come out to be minus 2.63. That's our critical value. I'm sorry, a test statistic. Okay. All right, good. So I need to come up with a decision. Remember, this is a left-tailed test, so let's just do a quick graph just for us to remember. So our test statistic, a critical value, was minus 1.363. So this defined the critical region here. This is alpha equals 0.1. That's the area under the curve for this region here. Our test statistic was minus 2.63, which puts us well within our critical region. Okay, so it's going to help us. So we're going to say our test statistic, right, which is minus 2.63, is less than our critical value, which is minus 1.363, okay, which means it's in our critical region, which means I can reject our null hypothesis, which means I can conclude that, you know, the yoga did something maybe. So I can say there is enough evidence to support the claim that yoga decreases weekly aspirin intake. Okay. Now, I just want to call your attention, the alpha level is kind of high. Remember, we always say our general rule of thumb is alpha should be at 0.05 or less, okay? So we changed our alpha to 0.05. It's possible, yeah, this is still a pretty low test statistic, right? So it's possible that we would still be within the critical region, just not as far into the critical region because our alpha level was really high. Just some things to keep in mind. Okay. There's that. All right. So let's think about, I'm going to make a note here. We want to use the p-value method, right? We always talk about how to use the p-value method. It's slightly different when we do our t-test because it's not like I can get the exact p-value like I did before when I had the z-test. So let's talk about how we would do using the p-value method with t-test. Because you will be asked to do p-value methods either in homework or on quizzes and tests and stuff. So now we'll say if our t-test value, for example, is equal to 2.056, say, okay, and let's say my sample size is equal to 11, and this is going to be right-tailed. I'm just giving you examples of what this will look like, a right-tailed test. So that means that my degree of freedom is my n minus 1, so it's going to equal to 10. Okay. So when I look up my t-test value, right? Let's take a look. So my degree of freedom equals 10. Where am I at? So my degree of freedom equals 10. And this is all my, I have to look along here for t-value. So my t-value is 2.056. So it's like 1.81 and 2.2, but I need 2.056. So it's not, these are t-values now, remember. So my t-value is somewhere in between these two values here, which corresponds to an alpha 0.05 and 0.025. So we no longer have a definite value for our p-value anymore to compare it with. I have a range of values for our p-value, right? So that's how I'm reading it here. Let's write that down. So then we say that our 2.056 falls between p-values of 1.812 and 2.228. Now these correspond to alpha values, right? For 1.812 that was 0.05, and for 2.28 this corresponds to 0.025. Okay, so what that means is I say that we have to say our p-value is between 0.05 and 0.025. Okay, I don't have a definite, I just have a range of values. So we're going to write it, I'm going to write it like this. So I'm going to say 0.025 is less than p, which is less than 0.05. Okay. So that means depending on the alpha level that I'm testing at for significance, we define our alpha level experimentally. So if I say that my alpha level equals 0.05, right, we could reject the null hypothesis because the p-value is less than alpha, right? This is p-value is less than 0.05. It's not less than or equal to, it's less than. Okay, let's say, let's see, if our alpha was equal to 0.01, we couldn't reject it, right? Because 0.01 is less than 0.025. Our p-value is somewhere between 0.025 and 0.05, right? But 0.01 is less than 0.025, so it's outside of our range. Could not reject our null hypothesis because our p-value, right, is greater than our alpha. Okay, so be careful. This would be 0.025 is greater than 0.01. Okay, so be careful. So we no longer have a definite value that we're comparing things with. We have a range of values. Okay, so let's try example 3. So example 3, we're going to use the p-value method. So example 3 says a physician claims that joggers have a maximal oxygen uptake that's greater than the average of all adults. Stands to reason they're respiring a lot more because they're doing heavy aerobic activity. So they do a random sample, n equals 15, random sample 15 joggers. And they found that the sample mean is 40.6 and a sample standard deviation of 6, right? This is milliliters per kilogram. If the average of all adults, this is our population mean, is 36.7, is there enough evidence to support the claim at the alpha 0.05 level? Okay, but watch, this is greater than, okay? So we're thinking about things in terms of a right-tailed test based on how things are being labeled here. We're going to use the p-value method, and we're going to assume the data is normally distributed, which allows us to use a t-test to compare stuff. All right, so let's write down we have. So our hypothesis is this. I've got my null hypothesis that the mean is equal to 36.7. That's our population, versus our alternative hypothesis, which says that the mean is greater than 36.7. Okay, this is our oxygen uptake. Okay, so we have to calculate out our test value, right? So our test value, that's my t equals x bar minus mean all over sample standard deviation all over our sample size square root. So I can plug things in. So my right here, my sample mean 40.6 minus my population all over my sample divided by radical 15. Okay. So I add, subtract, multiply, divide, and I get my t-value equal to 2.517. Okay. So remember, this is our t-value. I'm going to look this up to my degrees of freedom and finding the right t-value, and I'm going to try to find the corresponding alpha value at the top. This is alpha value at the top. All right. So our corresponding p-value. It's not going to be exact like it was with the z-test. So my degrees of freedom equals n minus 1. So that's 14. Okay, that's how I'm going to use on my graph. And I've got 2.517 that I need to look at. It's a right-tailed test, so I don't have to make anything negative. Okay. So so 14 and 2.5. Oh, so it falls between here and here, right? These two values. So degrees of freedom 14. I scooch across here, and I'm going 2.1448 to 2.6. Okay, and that's going to correspond to alpha of 0.025 and alpha of 0.01. Okay, so let's write down those numbers here. So this value falls between 0.1448, these are t values, and 2.624, okay, which correspond to alpha values of 0.025 and 0.01. Okay, so I'm going to use that to come up with a range of values for my p-value. So I'm going to say 0.01 is less than my p-value, which is less than 0.025. Okay, now I need to compare that with my alpha. Okay, remember, this gives us the area under the curve. Alpha represents the area under the curve. That's our probability. So my decision. So what I'm going to do is my alpha, we said the alpha was 0.05, right? So alpha 0.05 is greater than 0.025. So my alpha, right? If my alpha is bigger, remember how this looks, right? So this is our t-value here. This represents our alpha, okay? Our p-value, in this case, is going to be between here and here, say, for example. Okay, this is our p-value, okay? So what that means is, right, depending on where it starts, it could start here and go over, could start here and go over, okay? So what that means is our p-value is well within our critical region. But let's write it out. So we're going to reject our null hypothesis since our alpha equals 0.05, and that's greater than our p-value, our upper end of our p-value, upper end, 0.025, okay? We could even say p-value our p-value, which is less than 0.025. Okay. So that way we can write it in words. So there is enough evidence to support the claim. Let me write this up. To support the claim that joggers take in more oxygen. Okay. P-value method, right? But be careful. We don't have an exact value like we did when we did the z-test. We have a range of values now, okay, which is fine. All we have to do is we compare our alpha to the upper or lower range, okay? Is the alpha does this incorporate the alpha or not, okay? Alpha outside of that. Then remember what it means visually. This whole thing is our alpha, and our p-value in this case is well within our critical range. Okay. I'm going to put my example sheet away for a minute. All right, so let's talk about our z-test versus our p-test. How do we know when we should use one or the other? I put a little note on our Blackboard page. It's like at the bottom, I think, about sort of a general rule of thumb. If you'll notice some of the old test review sheets that come from previous instructors in different semesters, they do it slightly different. They take the absolute value of things they compare it to other values and stuff like that. I wouldn't worry about the absolute value, but just you can ignore the absolute value. Calculate things based on hypothesis, test value, critical value, decision making, just like we've been doing in class. Okay, so I'm going to use z-test versus t-test. Okay, some general rules of thumb. Okay, so basically, if our population standard deviation is known. Ooh, so if our population standard deviation is known, then we can use our z-test. Give information about the population, okay? Unless, if our n is less than 30, we can use our t-test. If the n is less than 30, the data have to be normally distributed. We can't make the assumption that it will be. It's really our population standard deviation, whether it's known or unknown, is kind of like our deciding factor. So if it's known, go ahead and use the z-test. If the n is less than 30, it has to be stated that the data is normally distributed. If it doesn't state that and the n is greater than 30, you can assume by the law of large numbers that the data is normally distributed and use the z-test, okay, if our population standard deviation is known. So if our population standard deviation is unknown, okay, but our n is greater than or equal to 30, we're still going to use the t-test. Because all we have is our sample. We have our sample standard deviation and our sample mean. That means I have to use the t-test. Okay. Luckily, we have our t-tables, right, that go up high in number in terms of our degrees of freedom. Okay. If the population standard deviation is unknown and our n is less than 30, definitely we're going to use the t-test. Okay. So it's basically still, we're kind of flipping our decision-making process on our sigma, okay? If the sigma is known, but we don't know that the data is normally distributed, and the n is less than 30, we should probably use the t-test, and then just use that population sigma in lieu of our sample sigma, because our n is so small, our confidence in those data isn't as high, okay? So it really flips on whether our population standard deviation is known. Example 4. So example 4 says, it's assumed that the mean systolic blood pressure is 120 milligrams of mercury, millimeters of mercury, sorry. And so in this test, they did this Honolulu heart study. It was like a test that they did. A sample of 100 people who lived in Honolulu had an average systolic blood pressure of 130.1 millimeters of mercury with a standard deviation of 21.21. Is the group systolic blood pressure significantly different from the general population at alpha 0.05? Okay, so let's see. Okay, so this is our general population. This is our sample population, our sample size. Okay, so let's see. Our n is pretty large. right? But we're still only given our population, right? And we have a population mean, but we don't have a population standard deviation. Let's write down all of our stuff. So our hypothesis is this. We have our null hypothesis that our mean is equal to 120. That comes from our general population. Versus our alternative hypothesis that the mean, right, is not equal to 120, right? They said, is it different, significantly different? They don't say, is it greater than, is it less than? They say, is it different, which means we're dealing with a two-tailed test. So I'm going to calculate, they don't say use p-value or anything, so I'm going to use a critical value. You can decide, if it doesn't state, like specifically to use the p-value method, you can use whichever method you want. Personally, I kind of default to the critical value, but if you like the p-value method better, go for it. I'll grade both. All right, so this is a two-tailed test. Right, so remember, right, we're taking our alpha and we're splitting it into 2. This is alpha over 2, this is alpha over 2 in this area under the curve. Because we need to find positive and negative t-values. Okay, so my degrees of freedom equals 99. That's n minus 1, makes it 99. And my alpha over 2, right? So my alpha is 0.05. I have to divide that by 2. Okay, so this is 0.025, and my degree of freedom is 99. I have to look that up on my table. I'm getting into a lot of large numbers. I'm approaching my z-curve anyway. But I'm right here. My degree of freedom is 99. My alpha is equal to 0.025. We're like right around here. Okay, so my t-value is going to be both positive and negative, 1.983. I just want to do a separate, I'll write this in pink. So on our z-table says for alpha over 2, the z-value is equal to plus or minus 1.96, right? So it's not too far off, right? So 1.983, 1.96. Okay, so just keep that in mind in terms of comparisons with our z-table. So see how as our sample number gets higher, we're approaching our z-table. The values are getting really similar. All right, so that means this is positive 1.983. This is negative 1.983 in terms of my t-values. Okay, that define my critical region. All right, so I need to come up with a test statistic based on my data. Okay, so I have to calculate t equals my sample minus my mean over my sample over my sample size. Okay, so let's write in our values. 130.1 minus 120 all over 21.21 all over radical 100. Okay, so I'm going to subtract, multiply, divide. Watch out if you're doing this on your calculator all in one full swoop that you have parentheses around the bottom. So my t-value equals 4.76. Whoa, that's like way off the chart, right? That's pretty good. Okay, so our decision. Okay, we're going to compare our t-statistic to the positive end, right? So if my critical value region gets defined as 1.983, my t-statistic was at 4.7. So I'm like way out here. Okay, so I'm definitely way off into that tail of my critical region. So my t-statistic, I'll say, I'm sorry, my decision is based on my test statistic, which was 4.76, is much greater than my positive critical value. Say positive critical value because this is a two-tailed test. Critical value, which was positive 1.983. So therefore, I can reject the null hypothesis and say definitely that there's a difference between those who participated in the Honolulu Heart Study, the blood pressure, and those in the general population, not in the Honolulu Heart Study. Okay. So let's also do, I'll do this in a different color. We'll do a p-value just so you can kind of see. Do this with a p-value. So our p-value, we're going to find our largest p-value is equal to 2.625 for our degree of freedom equals 99. I can't change the degree of freedom, so I still have to look at 99. I'm looking down here, 99, and my largest is right here, right at the end, and that corresponds to 0.005. Okay, so it's largest is this, which means that so let's write that out because this is a two-tailed test. So this is alpha over 2, which is 0.005. Okay, so to find alpha, I have to multiply that by 2. So this is 2 times 0.005, which is going to give me 0.01. Okay, so this defines our p-value. We're going to say our p-value is less than 0.01. Okay, so this is we're way off the end here. So now our decision, right, based on our critical value, okay, and now if we make our decision here with our p-value, this is in case you're asked to do it with p-value and you want to know how to do it, our p-value, we're going to say 0.01 is less than 0.05. So this is our p-value, less than our alpha. Okay, so therefore we can reject our null hypothesis because our p-value is well within our critical region value. Okay. Right, so there's enough evidence to say that the Honolulu, those who participated in the Honolulu heart study had blood pressures that were, much great. In this case, they're very different than the ones in the general population. All right. That's the end of example 4. I want to talk for a minute about using our t-test with confidence intervals, okay, and using confidence intervals to help make a decision about significance. So let's talk about confidence intervals. This is for when our population standard deviation is unknown. So we're going to use the t-distribution. Right. Remember before when we did our confidence intervals, we knew our population standard deviation. So we can come up with a confidence interval for our population mean. In this case, we just have our sample. So what I'm going to say, my confidence interval for t is going to look like this: my sample minus my t alpha over 2. Remember, our confidence intervals, right? We're talking about some kind of 95% confidence or 90% confidence or whatever. My confidence intervals are inherently two-sided, so it's always alpha over 2, whether it's z or t. Sample over radical n, and x bar plus t alpha over 2, sample over radical n. So this is my 1 minus alpha times 100% confidence interval. Right? So if my alpha is 0.05, I'm going to get 1 minus alpha, our 95% confidence interval, say for example, or 90% or 99, depending on what your alpha level is. This gives us a confidence interval that says I'm whatever, 95% confident that my population mean is between here and here. Okay, we can also use this to help us come up with a hypothesis testing. So we're going to talk about stuff like that. Right. So given this formula, these are also on your formula sheet, but you may want to just check it to make sure it's written in the way that you recognize. All right, so example 5, we have a random sample of high temperatures for 12 recent Thanksgiving days. So we went back 12 years. And these had an average of 42 degrees Fahrenheit, okay? We're going to assume that the variable is normally distributed and the standard deviation of the samples is 8 degrees Fahrenheit. Find the 95% confidence interval for the population mean. Okay, so we have our samples, we have our n, okay, and we have our sample standard deviation. So let's start kind of thinking about what's going on here. So I'm going to write down, take notes. My sample is 42 degrees, and I'll put my units, 42 degrees Fahrenheit. My sample standard deviation is 8. My degrees of freedom, right, is 12 minus 1, equal to 11. My population standard deviation is unknown, so I need to use the t-test, right? All I had was my sample standard deviation. Okay, so now let's look at it. So 95% confidence interval means I've got an alpha of 0.05, okay? So my confidence interval, I need to look at alpha over 2, 0.05 over 2, 0.025. Okay, so this is what I'm looking up on my table to get my appropriate t-value, okay? So my t, alpha over 2 for 11 degrees of freedom, okay, is going to look like 2.201. Okay, so I got that from my table. All right, so I'm pulling this out. Degrees of freedom equals 11, alpha equals 0.025. My t-value is 2.201. That's how I got that. Okay, so I'm going to plug this into my confidence interval. So x minus t alpha over 2 sample standard deviation all over that less than my mean, which is less than x bar plus t alpha over 2 for radical n. So now I'm going to plug in the values that we have. Okay, so this is 42 minus 2.201, right? This is 8 over radical 12, less than my mean, which is, my mean is going to be between these numbers here, 42 plus 2.201, 8 over radical 12. Okay, these should be the same numbers on either side because of symmetry. Okay, so I'm going to add, multiply, whatever, and I'm going to get 36.92 is less than mean, which is less than 47.08. That's my 95% confidence interval for the population mean of temperatures on Thanksgiving Day. So let's write that down in words so we can see. So we can say we can be 95% confident that the population mean for temperatures on Thanksgiving Day are between these values, 36.92 and 47.08 degrees Fahrenheit. Okay, I don't know exactly what the population mean of temperatures are for Thanksgiving Day. I just have a sample of 12 different years, and I've got a sample standard deviation, right? So I can be 95% confident that my population mean for temperatures on Thanksgiving Day in whatever region we're measuring this is between 36.9 and 47.08. That's how we read that. Okay. All right, now our last example for the video is, let's go back to the blood pressure example that we just did, the Honolulu Heart Study. And we want to use 95% confidence interval to help us make a decision, a hypothesis decision. Okay, so now let's write this down. So the population mean, we said our mu, this is from our hypothesis, was 120 milligrams of mercury. But what we had was our sample mean, which is 130.1, and we had our sample standard deviation, which was equal to, 21.21, and we had n equals 100. Okay, I'm just kind of reiterating the data that we had before. And we had an alpha 0.05, which is from our 95% confidence, 1 minus alpha times 100% gives us 95%. So that gives us an alpha of 0.05. Okay, but remember our confidence interval is two-tailed. Okay, so now I have to calculate alpha over 2, 0.05 divided by 2, which is 0.025. Okay, so given degree of freedom equals to 99, and alpha over 2 value of 0.025, I find my t statistic. This is t alpha over 2 for 99 degrees of freedom, and that's going to be 1.983. Okay, got that from my table. So we're going to plug that into our confidence interval, which I'll remind myself is my x bar plus or minus t alpha over 2 s over radical n. So let's plug in our data. So this is equal to 130.1 plus or minus 1.983 to 1.21 all over radical 100. Okay, this is writing it out like, right, 130.1 minus 1.93 times 21.21 over radical 100, and 130.1 plus 1.93. That defines the boundaries, right, of our confidence interval. So I'm going to add this up. This is 130.1 plus or minus 4.21, which means that our confidence interval, I can write it as this. So if I do this out, I'm going to go 125.89. So this is 130.1 minus 4.21, less than, it's less than my mean, which is less than 130.1 plus 4.21, 134.31. Okay, which means I can say that my confidence interval is equal to 125.89 to 134.31. This is my 95% confidence interval. Okay. Now, what I need to do before we said, what's our 95% confidence interval of our population mean? Okay. Now, to do this as a way of judging our hypothesis, do I accept or reject my hypothesis, right? I'm going to take a look at this interval here, and I'm going to ask myself, does this 95% confidence interval contain our population mean, which was 120? 120, 125.89 to 134.31. 120 is like less than 125. So the answer is no. The 95% confidence interval does not contain what our null hypothesis was. Our null hypothesis, our mean was equal to 120, which means that I can reject my null hypothesis. Okay, therefore, I can reject our null hypothesis because it's not within my confidence interval. So I'm going to reject it. Okay. All right. So what I'd like to do is I'm going to stop here. And when we meet next time, we're going to talk about tests for variances, right? So right now we just talked about means, and we're using our t-test for that. And then when we meet next time, this is still within the chapter 72, 73, 74 bit, okay? And we're going to talk about our test for variances, which also means that we're working into what we call a chi-squared distribution. So I'll put up a chi-squared table as well on the Blackboard page. You guys can take a look for that, okay? See you later.